realize that we have a lot of backgrounds. So I will not speak about any technicality today. And I will just basically count a history or speak about a history of one paper or one work I have been working since my PhD here in NeuroMat. Well, the point is I'm a mathematician by definition. I came from math, right? So I decided to come to USP because I didn't want to do math just to do math anymore. I would like to work in more realistic problems. So I decided to come and took a PhD in statistics. So for those which are not mathematicians, believe me, math is different from the statistics. There are different stuffs, right? So, and when I arrived here was the beginning of NeuroMat maybe. Well, the project was starting, and I decided to work with Antonio, and then I was a mathematician, right? So I have math. I will try to do something which is the most formal math we will see today in my talk. So we have here, I was here in math, and then I decided to come and see what happens in statistics. And with Antonio, usually we work with stochastic process, which is some way here. Good. Stochastic process is something which we can handle. It's math, theory, probability theory, right? And then NeuroMat comes. And we decide to work with problems based in neuroscience. So we have something in here, right? Neuro. Okay. And then we have here stochastic process based on some problems in neuroscience. Good, I can deal with this. I can do math with this. Good. The point is, when we start to work with some very multidisciplinary stuffs, most of the case you are not able to stay here, right? And then during my PhD, I had to work like in other areas. For instance, during the beginning of this project I will talk about, well, this project is basically you give some stochastic stimuli. So stochastic, we are here. So my stimuli is here. I give some stochastic stimuli to people, and we record their brain answer, right? The point is, when we decide to do this, you have to collect data, right? And as a mathematician, I never think about that. When we are here, we don't have to think about that. But when we are trying to do something new and starting a new project, we have to think about this. So during my PhD, I stayed 2 weeks in Rio in the Claudius Vargas lab, collecting data. I'm a mathematician, but I was basically here, like EEG, record, I don't know how to say that, collecting, something like that. So I was here. So this is new, completely new for a mathematician, right? Are you able to see here? No? Oh, so nice picture. A lot of work. So, come on. Can you imagine, right? It's not part of this part. So this is completely new for me, which came from the math part, right? And then, okay, I went to Rio and we have this data, and then I come back with my data and I was really happy. So now we will apply this part, right, in my data. And then you open your data and you look at, and you realize that you are not able even to read the data. Because there is something called processing or pre-processing. Before doing statistics, before doing analysis, you have to process your data, filter your data and all this stuff. And then there is another part of my picture. I'm not sure if I'm able to do it. I will do it in another color, which comes maybe here, which comes from the computer science. And then I have to learn something here, again. Because as a mathematician, I really believe that I would put my data in the computer and look in the data and this is it. And then I realized that not. And someone told me, look, you have to use some package from MATLAB. I didn't know what was MATLAB at that point. Really, I never had any experience with any kind of programming. So they told me and they teach me that actually I have to have this program MATLAB and I have to download some new package, which was able, okay, this part was good. I just have to learn how to press some buttons and I will be able to do this part, right? The processing of my data. Good. This is about computational science maybe and neuroscience, okay? Nothing new. Now I'm able to look in my data. I look in my data, and now we can come back in this part, the part that we are supposed to stay when you are a mathematician or in a statistical program, right? And then we model the problem. We have a new statistical approach for this problem, and we prove theorems. You do math. Great, we are here, the part that supposed to be good, right? And then you have to apply your data to this part. And then, again, as a mathematician, you think, okay, I have a theorem, which is theoretical. I have a data that I can read now, but you have to apply your theorem to your data. And then again, you have to write codes. And then it's not here anymore because there is no package MATLAB to help you to download and do it. So you have to write your own codes. And then you are something maybe here. So this is the part that I have to learn it by myself or with help of a few people that you have to do the modeling, do the statistical approach of your modeling and write your own codes to apply it to our theorems and see your results. And this is not something that you do it doing math only or doing only statistics or doing only computer science or doing only neuroscience. And it's not that I'm very clever person with a lot of skills. It's not the point. It's not because I'm more intelligent than anyone here. My point is I do it as a mathematician, not as a computer science person. Noslen look in my codes nowadays, and usually she took some code with 200 lines, and then she just took everything away and write again in 20 lines. It's the same thing, the same thing, but she can do it in a very best way that I do. My point here is I was able to do all these stuffs because I'm working in a project which is very, very multidisciplinary. And I think part of this, this meeting is about that, right? We have physicists, statisticians, mathematicians, computer science people, neurobiologists. How I say that? Patricia is physiotherapist, so without this kind of exchange, I will never be able to hit this part of. And even though when I arrived here, I didn't know what is MATLAB, now I'm writing a paper about a package for MATLAB. You see what I mean? So I think this is a very good opportunity to all of us to learn, and it doesn't matter how your background, you will be able to do it in many parts of this, this very strange picture. You can learn and you can help science and in some point in all of these parts. So this is basically what I have to say to you. It's really short. I just want to tell you what I did as a mathematician. I started as a mathematician and what I was able to do it in my history here in the project. And I'd really like you to enjoy this meeting and exchange experiences because this is really nice. At least for me, I think this is really nice, really important, and I think science would be much, much efficient if all projects, all scientists, all people was able to walk around all these parts of these pictures, okay? I don't think you have questions, right? There is no technicality, so I don't think you have questions, right? What? No, for a mathematician, this is really big. Come on. Collecting data, EEG data, this is really big.
So now everyone will be extremely motivated to listen to the talk of the day. So we're going to start with Noslen Hernández, who did a PhD in the University of Havana, is that right? Yes, in computer science. and who's doing her postdoc at NeuroMat at the moment. And she's going to talk about, we're going to see, she's going to talk about retrieving the structure of probabilistic sequences of auditory stimuli from EEG data. So this is technical.
Congelar, peraí, ver sua senha. Cadê o... Conectar na internet também, né? É, no seu drive, no seu... Clica duas vezes. Só aumenta a tela. Aqui, ó, abrir com... Aí tem que começar a iniciar. Oi? É, deveria ser. Oi? Não, não tá. Não achei aqui. Não sei.
Okay, so the file has now been found, and we're going to start the presentation.
Ok.
You on the mic?
Tem outro livro?
Não.
No? Okay.
Vou colocar aqui, tá? Não? Tem. Okay. Okay, good morning to everybody. I'm going to present here some results of a paper we have been working on it during the last year. This work is in collaboration with Raimundo, Aline, Guilherme, Ricardo Freeman, Antonio, and Claudia Vargas. And in fact, all those co-authors, except Raimundo, has been working in the theoretical framework behind this research for some years. And these theoretical results are already published in a mathematical journal. And what we have done during the last time is a neuroscience, is a version of this of those results for a neuroscience journal, which are showing mainly the results on the real data and as an introduction, it has been suggested from a long time that the brain is able to learn some statistical regularity from a sequence of stimuli, and this is people to make decision making, and we can see this we can see and realize evidence of this fact in many activity, like for example, learning a language or learning a piece of music. And when we look at the literature, there are some words trying to showing that this conjecture is true. And we have some work mainly based in showing that the brain is sensitive to some simple statistical regularity, like item frequency and transition probability. These are mainly in this reference that I put here. And more recently, there are some other works showing that humans, in fact, are sensitive to high order temporal statistics. That means in real life, we found some statistical regularity in many activities that are more complex than just item frequency and transition probability. And this work go a step ahead in this direction. We mainly apply a new statistical framework to try to show that the brain is able to learn these more complex structures. And to do that, we propose a new experimental protocol that I will describe in the next slide. So the experiment consists on a person listen to a sequence of auditory stimuli, and these stimuli are of three types. We have a strong weak, we have a weak beat, and we have a silent unit. And with these three kinds of stimuli, we generate a sequence with some statistical regularity. And during the exposure of this sequence of stimuli, we measure some EEG signals from the brain. And this sequence of stimuli have a specific structure that I will explain soon. And the conjecture is that our conjecture is that the brain is able to identify the structure, the probabilistic structure used to generate the sequence of stimuli. I will explain more detail what is this structure. We use context tree models to generate that sequence of stimulus. So we have a specific question. That is whether we can retrieve from the EEG sequence the context tree used to generate the sequence of stimuli. Okay, and I will explain now which is the structure of this sequence of stimuli intuitively, and then I will put some definitions to be more formal. I will use, in the experiment, we have two conditions, two kind of context tree model. We use one of them to try to give the intuition of this probabilistic structure. So we have three kind of stimuli that we will represent by the symbol 0, 1, and 2. And suppose we have a deterministic sequence that a deterministic sequence in the following way. We listen a strong beat, then weak beat with big, strong, weak, strong, weak. And then with a small probability, we can replace any of the weak beat by a silent unit, which will be denoted by this 0. So we can have a sequence of this way: 2, 1, 0. 2, 0, 0, 2, 0, 1, 2, 1, 1. Okay, and And then in this kind of sequence, to generate the next symbol, the generation of the we will depend on the pass, né? And on this, but this pass is not of its length. So, for example, each time I see a strong beat, né? I know I know which is the next symbols that follow a strong beat. Okay. And this part of the past that determine the generation of the next symbols we call context, and we will see later a more formal definition. Okay, so I will put here the present to be more easy. So if I'm here and I want to know which symbol is going to be generated here, I go one step back in the past. And if I saw a symbol 2, I know I know exactly which symbol can be generated here, because after a 2, I can see a 0 with a small probability, or I can see with probability epsilon, or I can see a 1 with probability 1 minus epsilon. Okay, so I have here a transition probability which give to me exactly which kind of symbol I can observe here. But for example, if I observe if the immediately past symbol is a 1, then I have to go a step back into the past, because I can be in this situation, or in this situation. Okay? So I have to go a step back into the past, and I will have, as this past that determine the generation of the next symbol, I will have 2, 1, 1, 1, and 0, 1. And a similar behavior occur when immediately in one step back, I have the symbol 0. Okay, so I will have here, I observe the 0, and I will have to go one step back in the past, and then if I observe 0, 0, 0, 1, or 2, 1, 0, 0, 1, 0, and 2, 0, then I will have a transition probability governing the generation of the next symbols. Okay. Well, more formally, this pass sequence will determine the generation of the next symbol I'll call context, and this structure that I exemplify here is called a context tree, and well, formally we will have a finite alphabet. We will have to define context tree, we would define what is a suffix sequence, okay? One sequence is suffix of another. Is there exists another sequence such that satisfies this condition? Okay, for example, here I have this sequence, and 1, 1 is a suffix of this complete sequence, and 1, 1 is a suffix also of this sequence, okay? And then a context tree is a set of sequence that satisfies these two conditions, okay? No element of the context tree, I mean, no context can be a suffix of another context, and I can replace one context by a proper suffix without violating this first property. This context tree jointly with the transition probability associated to the context, we will call probabilistic context tree. And then a context tree model, which is this kind of second I was trying to exemplify. A context tree model is a stochastic chain in which the generation of the next next symbol will depend only on the transition probability associated to the context associated to the past sequence. I mean, the only thing I have to know to generate the next symbol is to see which is the context associated to this past sequence, and then generate the next symbol according to the transition probability associated to that context. Well, in the experiment, we use two different context tree models. One we call ternary condition, and is this example I was explaining here. And the second one is called quaternary condition. Quaternary condition is similar, but instead of beginning with this deterministic sequence, we have a sequence of this kind, 2, 1, 0. Okay, in the quaternary condition, we have the following deterministic sequence, 2, 1, 0, 1, 2, 1, 0, 1. And then with a small probability epsilon, we replace any of the weak units by a silent unit. So we can have sequence of the type 2, 0, 0, 1, 2, 1, 0, 0, and so on. Okay, and this is the context tree representing this context tree. This is the context tree we use to generate this context tree model, and this is the family of transition probability associated to those contexts. Okay, in the experiment, we had 19 participants, and for each participant, we record EEG signal from 18 different electrodes. So, and this is done for this both condition that I had explained. So, for each participant and each electrode, we have a data set of this type. Okay, this means the sequence of stimuli is the X, okay? And associated to each sequence of stimuli, we have a piece of EEG signal. I mean, each time the participant listen a beat, we are measuring an EEG signals, né? And then this EEG signal is segmented and preprocessed, and we end up with a piece of EEG corresponding to each auditory unit. And this is the data set we are representing there. This is the X sequence, which is the context tree model, and this is the response sequence, which are a piece or chunk of EEG functions. And we have this for each participant and each electrode. And then on this data, we apply a statistical model selection procedure. We was introduced in the paper already published. And the objective if to this model selection procedure will give us a result, an estimate of a context tree from this data set. And we will compare, we will see if this context tree match the context tree that generate the sequence of stimuli. Okay, the theoretical model, okay, this statistical model selection procedure was what this statistical model selection procedure does is to estimate the parameter of a new kind of stochastic process that was introduced in the theoretical paper, which is called sequence of random objects driven by context-free model. And the idea behind this kind of object is the following. You have two sequences. Okay, you will have a bivariate sequence in which one sequence, the input sequence, is a context-free model generated by a probabilistic context tree, and the second sequence, the response sequence, is a sequence of random objects which satisfy the following condition. The objects in the sequence are conditionally independent given the past sequence of stimuli. And the law of these objects are determined mainly by the context associated to the past sequence of stimuli, okay? So the only thing I have to, so the generation of this response object will be determined by a distribution indexed by the context of the sequence of stimuli, by the context of the context tree that generates the sequence of stimuli, okay? And I will explain then the statistical model selection procedure on this bivariate chain to estimate context tree from this kind of object. Well, we begin segmenting the EEG signal as I explained. Then we take the complete context tree of a given height. Here we use height 3. A complete context tree is a tree in which we have all the sequence of length, in this case 3, that appears in the sequence of a stimuli. I mean, I see my sequence of a stimuli, I see all the possible sequence of length 3 that appear in the sequence of a stimuli, and these are the contexts in the complete context tree, okay? And then we begin a pruning procedure on this tree. And the pruning procedure consists mainly in applying a statistical test on each terminal branch. I take this branch, I apply a statistical test. If the null hypothesis is rejected, I will cut the branch, prune the branch. If it is not rejected, I keep the branch. Now, to do this statistical test, what we do? We take the EEG segments, all the EEG segments associated to the leaf of a given branch. For example, here we look in the sequence of stimuli all the times 0, 1, 2 appears, which are marked in green. And we will have a set of EEG functions associated to this string. And we do the same thing for 1, 1, 2, and we will have a set of EEG functions associated to this other string. And then the statistical test consists in checking the null hypothesis that they allow the distribution of these two sets of functions are the same. I mean, if these two sets of functions were generated by the same law. And to test this null hypothesis, it was used a method called projective method, which was introduced in a paper of Cuesta, Freiman, and other name that I don't remember now, in 2006. And this projective method we do is the following. Each function in the set of functions, we project in a random direction, and we use the projection, which is a real number, to compare if the law of this set of projection are the same. And here in the real, and here with these two set of real numbers, we use any statistical test to compare distribution. In this case, we use Kolmogorov-Smirnov test. The theoretical results behind this method say that if we don't reject the null hypothesis that the distribution of these two sets of real numbers are the same, then we we don't reject the null hypothesis that the two sets of functions have were generated by the same law. Well, this is a pseudocode for what I have explained in the picture, and then okay, when we apply this model selection procedure to each electrode and each participant, we end up with a set of context tree for each electrode. And in each context tree we obtain each context tree is, each of these context trees is one for each participant, okay? Because we have the same electrode in all participants, and then we have one context tree for each participant. And one thing that we want to do was to summarize in some way this set of context tree in order to have some idea of what is happening in a given electrode, okay, across all participants. And to do that, we introduce what we call a mode context tree. And this mode context tree is defined as follows. We count the number of times each sequence, a given sequence will be in this mode context tree, would be a context in this mode context tree, if the number of times it's appear as a context on each of the tree of this set is greater than the maximum number of times that any of the sequence from which he is a suffix appears in the greater in the sequence. Let me suppose I have a set of 3 context trees. Then I count. I have a tree with contain all these possible nodes, and I count the number of time. I count the number of times this string was a context on each tree, 3 times, and I put this 3 here. I count the number of times this was a context 2 times, and I put the frequency here. And in this way, I have a frequency on each node of this tree. And then I choose as a context this node, if its frequency is greater than the maximum frequency I found in this branch, okay? Well, these are examples of this kind of computation on some of the electrodes. This is the complete tree and the frequency, and in red are the branch the context of the mode context tree. And these are the results for the quaternary condition. Okay. On each electrode, we have the mode context tree, and we use this. Sorry, key is missing 1 minus this. Okay, it's 1 minus this. This is a kind of similarity function, just to see the similarity between the tree that generates the sequence of stimuli and the mode context tree that we obtain on each electrode. And the color scale indicate the darker the green, the more similarity is to the tree that generates the source, and the darker the pink, the more dissimilarity. And well, for the quaternary conditions, we have that we obtain in most of frontal electrode the same context tree that generate the sequence of stimuli. Also, we obtain the same the same context tree that generates the sequence of stimuli in these two parietal and temporal electrodes. The other two frontal electrodes has a structure very similar to the structure of the source. Here is missing the third order branch, and here is missing this branch. Some statistics we can see, despite the variability of the tree around the scalp. For example, the context 2 was presented in all the mode context tree, and the branch 0, 1, 2, 1 was really well estimated also. One thing that we notice is that this third order branch is missing above all in this region. We do the same for the ternary condition. In the ternary condition, the results were a little worse than in the quaternary condition. We obtained exactly the context tree that generates the sequence of stimuli in 3 electrodes, but in most of the electrode, we can see this kind of structure which is very similar to the structure that generates the sequence of stimuli. The only branch that is missing is the 0, 0, 1, 0, and 2, 0 branch. And now, very briefly, how some of the results we obtain compare with what we can find in the literature. Well, in several previous research had shown that many previous results have shown that the brain is able to learn first order temporal dependencies and higher order temporal dependencies. And with our experimental protocol and our results, we can confirm both things, because we have higher order temporal dependencies as this that appear in these branches of the two conditions. And we have also first order temporal dependencies, for example, 2 as a context. But with this experimental protocol, we go beyond those previous reports, because we can identify the SAT structure that the participant is learning or is identifying. Another kind of results that is very discussed in literatures is that most of the statistical learning paradigms has mostly relied on surprise signals. I mean, they compare when they compare the signal corresponding to a surprise stimuli and to a common stimuli. And in our experimental protocol, we can see in both conditions some branches with the recovery of those branches can be explained by the presence of a surprise signals, but we have some other branches which cannot be explained by the presence of a surprise signal, because the presence of the current stimuli given the past is equally expected for all the contexts in a branch. So we have also these 2 conditions in the experimental protocol contain these two situations. And another thing that is congruent with what the literature reveals is that the best results are obtained in the prefrontal region. And this can be explained by this fact, and this can be evidence in our results above all in the quaternary condition, in which we obtain for almost all the prefrontal electrodes, the SAT context tree that generate the sequence of stimuli. Well, that's all. Thank you.
Thanks a lot. So, does anyone have a question? So, no question. I do have a quick one, which is kind of irrelevant, but it's curiosity. When the participant, so they kind of detect the patterns, is it unconscious, or can they tell you what pattern did they detect?
No, for participants, during the instruction. For participants in the instruction, it is not safe to participant anything about the structure
yes, but
behind.
They may detect by themselves that there is a pattern.
Sorry?
Maybe they detect by themselves that there is a pattern in the sound. Or maybe they don't, and it's just a subconscious process.
We don't ask participants to do any task.
Yes, but do they tell you? You don't ask them at the end.
At the end, if we
yes.
ask if they detect or not detect, I don't know. We ask.
Yes.
Not if they realize that there is a pattern, but at least if they are able to realize that we have different patterns. Like if they are able to see that we have ternary, quaternary stuffs, and when we have some, when we erase a weak bit, we also make like a test with them, saying, "Oh, can you realize that's missing something?" And then we have some comportamental stuff, part of the experiment, where they have to say where when they think there is missing something. So we can have some measurement that if they realize that there is something missing or not, at least.
But sometimes they do not know consciously, but you can detect
Yeah,
that.
sometimes it's completely wrong. They think there's missing something which is not, but most of the case they are able to see when, at least when there's missing something.
Okay, thanks.
But this kind of information is not taken into account in
This
kind of information is not taken into account in the analysis.
So in the beginning, when you, Claudia and I, Aline, think about the experiment, so we are trying to think about the type of stimuli we are going to present. So I was at the INDC in Rio, and then there was a student there, Claudia's student, and then I decided to check if the kind of stimuli we are presenting was something good. Please take it for me. So I told her, look, listen. And so on, and ask her, did you get the structure? I said, no, I don't know. Think again. And then she said, well, you did. So, and then I realized that she understood something. She was unable to produce because she was not trained as a musician, but she was so I was very happy. Okay, that's it. Second word, von Helmholtz, when he started thinking about this, he was one of the first one, maybe the first one, he called this unconscious inference.
I don't think I noticed it if you told how many stimuli did you present?
Around 800.
800.
Yes.
Okay. It is something that I would like to see how the context tree estimation changes if you use less or more trials. It's something I would like really to see, because I'm trying to develop the setup now, and I'm thinking about the context tree models, and the number of trials in my work, because it's a decision-making scenario, is something very, very delicate. So I think it's a good thing to do. So you take different number of trials and see how this changes your estimate of the context tree model.
A suggestion for people in computational neuroscience to make models of learning by the brain in which this kind of phenomena could be simulated. So, of course, I don't know how to do it, but it's a good question.
Currently, Newton from my lab and Noslen, who just presented, are working on this. They are using the Portens-Diesman cortical microcircuit model to investigate whether this phenomenon can be observed in a simulation of a network of neurons. And we don't have learning yet there, but the initial conjecture is that the structure of the network, which is complex, it has about 80,000 neurons, might be sufficient for the detection of the context tree from the measurements. This is the first conjecture, as we have discussed it here before. If not possible, then we have to add learning and other structures. But the initial thing is the network by itself complex enough for us as experimenters to be able to detect, to infer the type of, to use the methods and infer the context tree? So this is the question. So I think, well, Newton is not going to talk about this today, no? But yeah, I'm just writing the report of SimLab, and next week we'll have a meeting, and then we'll discuss this. But we're working on this.
Okay, thanks a lot. So as we're running late, we're going to go to the next talk. And the next talk is going to be by Fernando Araujo Najman, that you probably already know, as he's a PhD at NeuroMat, and he's going to talk to us about statistical model selection in the brain and its electrophysiological signatures.
Test. I think it's opening. Well, while it's open, I would like to, as one of the organizers, I would like to thank everybody for coming. And I hope that is a good chance to everybody to understand what each other is doing. And because there's a lot of people, like Aline very well put, a lot of interdisciplinarity. So let's use this opportunity. So my name is Fernando Najman. I'm a PhD student here by the Bioinformatics program with Antonio Galvez as my advisor. And the title of my thesis is Statistical Model Selection in the Brain and its Electrophysiological Signatures. There is a meaning, a definition for each term, but the general idea is we are assuming that the brain does something called statistical model selection, that is statistics, and that we can measure this by looking at the electric physiological data that the brain produces. Okay, that's not what I was expecting. Anyone knows how to put this on full screen? F5. Okay, thank you. So what I'm going to talk about now is an extension of what was just presented by Noslen. It's a continuation on the same subject and based on the same experimental paradigm. So this, this is based on the paper that I read published by Aline Freiman Galvez Ost Vargas. And we use the same paradigm and the same data. So I see this paradigm as a continuation of a classical field of study in psychology called psychophysics. Psychophysics is a field that started in the 19th century, about the second half of the 19th century by the first guy to coin the term, that gave this name, is a guy called now Gustav Fechner. Basically, this guy understands physics, And he had a simple question. If I take some stimuli that I know how to describe with a physical model, for example, luminosity or sound intensity, and I present it to a subject, how does these physical characteristics of the stimuli can be perceived by the subject? What this tells us about the brain and how it functions. So he wrote a book, and another guy who read it was a guy called Hermann von Helmholtz, a physicist, Helmholtz, I think. He was a physicist and a really important one. He was the advisor of Hertz, the guy from the Unity. He was the advisor of another guy who was another founding father of experimental psychology, the advisor of Planck, Max Planck. So he has a fitting in each area. And something that he found really interesting is how he could do this communication between physics and neuroscience that didn't have this name at the time, and he started to studying the same thing. He give, for example, 2 pebbles to someone with different weights that you could measure by the physical model of weights of force of newtons. And he just tried to ask people when could they differentiate between the 2 pebbles. And he found, this 2 and his student found, for example, a logarithmic relation between the weights and the perception of people. They could only differentiate when there's a logarithmic difference between them. But this field is still studied today, a really interesting field, but it is based on the classical physical models that are deterministic. Not like, they knew probability, there is still a lot of mathematical advances that happened only in the 20th century, but he knew something. Like I said, he was the advisor on the main quantum physicists. But they still didn't have the models that we have today. So they focused mostly on deterministic models of sound intensity and so on. So in the study of neuroscience, that stayed the rule for almost 100 years. Until the 70s, when this starts to change a little bit in small steps. So there, in the 70s, when the first models with stochasticity on the stimuli were developed and start to be used to study neuroscience. So the first paradigm that I know of that uses some stochastic model is the known audible paradigm. This paradigm, you give 2 sounds. It doesn't need to be sounds, but usually it is. And you choose 2 tones, usually tone 0 and tone 1. These are just symbols to represent each sound. And you have a probability associated with each one. So you have a probability of seeing a 0 is, I don't know, alpha, and a probability of seeing 1 is 1 minus alpha. And you generate a sequence using this measure, probability measure. So you have something like 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 1. And they used, and you can see that this sequence, the events are independent of each other, and they have an identical distribution. They are IID. That means that what's going to happen doesn't depend on the past. You just have a surprise if something happened or not, because that's all the information you have. And they studied this using EEG. A famous guy in this field called Nathan, I don't know if I'm butchering his name, but he even gave a name to a difference in the means of this EEG signal that you capture when you give a probable event and an improbable event. They do this by taking all the EEGs that happened after a 0, summing them, taking the average, taking all EEGs after the 1, taking the average, and seeing if this average is different. So it's a difference in mean. And they found one around 200 milliseconds after each sound that represents the surprise. And if they change what 1 and 0 means, if it's for example, a tone on a clap or something, you can still keep finding this effect. So it's assumed that it's related to the probability of happening, not to the physical characteristics. So here we're expanding this paradigm to the context theory paradigm, as I'm calling it. That we use the context theory that I knew Noslen would present, so I'm using a little bit the information she presents here to do my presentation. And here, when you talk about any sequence that is not IID, we start to have, well, that's not independent, we need a tree or something about the past that gives us information about what's going to happen next. These open new questions about how the brain works. This is a question you can't do with the audible paradigm. So here we start to then the people from NeuroMat that's the first obvious question. How does this tree appears in the data? And they recover the tree. So here I'm also I'm collecting new data. And this data changes one of the difference in my experiment, it changes the physical nature of the sounds I'm giving. In the first experiment were claps, right? A strong clap, a weak clap, and silence. Here I'm giving 3 tones, pure sine frequencies. And I choose, these numbers may seem weird, but they are the numbers, these frequencies represent the 3 notes of a major A triad. So this is one of the reasons I'm doing this, because I think it's a really good model to study musical cognition, and it's the same idea. So here I'm calling instead of 0, 1, and 2, A, C, and E. That's A, it's from the notes, usually called La, A, Do, C, and Mi, E. So I keep these notes. So my tree, I'm not showing here the probability measures associated, only the tree. And my tree as the previous experiment. Okay. And you see that here you get some sequence, example of a small part of the sequence generated by this tree. That's A, C, A, C, A. But this is still abstract. So I will just play for you if I, let's see. Nope, that should be playing something. Thais? Maybe the microphones are taking the sound slot. Okay, maybe I will left this for the end. But this keeps a small melody. It's not exactly music, it's a simplification. The notes are really more frequencies, and of course, music is really complicated. This is a simplification of the same idea, so we can start somewhere. Maybe it's the volume of the computer, okay. Which I still don't know how to. Anyone's here? No, it's max. It's probably the microphone, so I would guess. Okay. So I'm actually collecting data using 2 trees. This one and this one, the same ones used in the previous experiments. This one actually is really easy to imagine because a waltz is something like tu ta ta tu ta ta tu ta ta. When it's not in the most usual sequence of events. So I'm still using the same idea that I have 2 sequences. Hey, 2 sequences, a sound sequence that in my case will be something like E, A, and associated with, I have a EEG that happens after each sound, which I call Y. And Y is a EEG signal. Here I'm focusing only, I'm looking at each electrode independently. So a Y is the data for only one electrode. And this data you can think of, at least for now, as a vector of real numbers with D dimensions. That's this D is the sampling rate. So it's a really big dimension. I'm collecting at a sample rate of 2,500 hertz, which is more than I usually do. But I want you to see the effect of the sampling rate on that, so I usually subsample this. And the experimental parameters, I have a 4,000 sounds. For this X has a 4,000 length of units. And the time between the 2 beeps, the 2 events, the start of a note and the beginning of the next note, is almost half second, 0.5. In the experiment, we ask the participants to remain with their eyes closed, remain still as possible, so they don't have as much muscle artifacts. Each sound is actually starts, there's a half second between them, but each sound is actually itself a beep, a really quick beep of 0.075 seconds, 75 milliseconds. We interrupt those ramps with a technicality we won't get here, but it's not, it's usual to do. And we did that in 4 blocks, which each block with 1,000 sounds, and that's a duration of about 7 minutes. And this allows us also to see what the sampling size will affect, because now we have more samples of each context in this experiment. But now getting where what I did is different from before. Well, we are assuming that the brain understands the tree. What do we mean by that? We mean that each context will be associated with a different EEG law. The brain will work differently when you present a different context, if it understands it. So the EEG law, I mean the rules that generate the EEG should be different for each context. Because we assume that when the brain treats something different, the electroactivity will be different. That's really the usual paradigm. So how do we retrieve this information? Here we'll be doing something different. Noslen presented a projective method. That's a way, together with the context tree pruning method, that allows you to retrieve the best tree to approximate. But here we use a new methodology to try to test this hypothesis that we consider extension, because it also allows us to ask different questions and see what happens when it is not close to it, when it does not approximate the tree. This idea was, so we had this idea based on a fact that we realized about the 2 trees that we used. In these trees, if I call Cn the context of the sequence until the point n, in both of the trees, they have some really interesting property. This Cn is always equal to the previous context plus the next symbol, or the context is the symbol itself. So let's see in a tree. So in this sequence, the volts, or E is the context. So if E happens, the symbol itself is the context. Or if, for example, I see C, the new context is the previous context, that was E plus C. Okay? So this means that the sequence Cn is a order 1 Markov chain. If you look at the leaves, it only depends on the previous context. If you know the information, you only need to look at the previous information, size. Okay. And that means that we can use this to retrieve the information. That use a method we call clusters or clustering. This method I will need to explain before telling how to do it. You need to wait a second. You have a distance between 2 signals or 2 things that you can use. It's a really general method. And here I give an example of a hierarchical clustering. If you take a set of points, so if I write it here, you can see. I assume that, yes, okay. So I have a set of points, I have a space, and a set of points. And I have now, for example, 1, 2, 3, 4, 6, 7, 8, 9 points. And I take the two closest together. I don't know, these 2. And I put them in the same cluster. Then I do it again. These 2 are the closest. Then I do it again, and I see the closest one is this, and this become a cluster. I do this to the point to get k clusters. Which numbers k I will get later, but so you do this and you cluster together the data, and this is a good unsupervised method to see how many types of things you have in your data, how many, and a good way to try to find the number of laws. That's what we want. So if to test the conjecture that each context has a law associated with, let's assume that we have a k number of clusters, and we assign each sign to its cluster, to one of these clusters. So here I had x, y, and now I have a new random sequence that I can call I, where I is the index of where this EEG fault. So for example, if I have 2 clusters, this one is in the first cluster, I have a 1 here. This one falls in the second cluster, you have a 2. This one also falls in the second cluster in this arbitrary example, and also fall 2. Here I have You see that depends on the number of clusters, k. So I put here 2. That means usually I do yk, k. And if I do that, and we assume that, so I have this new sequence, and this allows us to identify the number of laws in EEG using this object. How? Well, we assume that if each EEG falls in the right class, the Y will have a sequence, right? We have some memory. But if each one is generated by a different context, and the sequence of context, like I said, is a Markov order 1, that means that this sequence should have order 1, because the signals are having all the necessary information. If I have all the necessary information, I can go to one step to the other one. I just need to see where I was with all the information and go to next step. So that's the general idea, the new way to propose. It's just really interesting to see what happens when in some case that they don't recover the tree, exactly tree, for example. There's new extensions to what we can do with this. We assume that, so we can find the right number of laws with this, because if I have the right number, I will have a memory 1. If I have more than the necessary information, that means if I using a larger k than I need, I still have order 1. But if I have put something, 2 different signals in the same class, I start to mislabeling them, I have a loss of memory, they call it. Basically, that means that sequence will most likely go to infinite memory, because I will lose information as start to understand what's happening. I have to go back, with no bounds to how back I need to go to understand where I am. Well, now to the challenges that I'm facing now. I'm focusing on the things I'm working right now. There's some preliminary results I will not present today, but I will talk about the challenges. Maybe someone has some good ideas. We can see if anyone can help. The first question, what distance to use? Here I made it looks really simple, right? I just put points together in a 2-dimensional Euclidean space that I draw. But I have data that's vectors in a really high dimension. What's a good way to see if they are close or distant? What's a good way to see if they are similar or different? What we mean by similar or different? Well, one usual way is to use the Euclidean distance. The difference that's equivalent with some scaling factor to the difference in the averages. That's, like I mentioned before, what people in the EEG community most of time does. With the ERP, sorry, I didn't mention before. ERP it's relate potentials. These are the name to these averages, as I mentioned before. So this is usually what they would do. They would take these averages and see the distance between them, because difference between averages is the Euclidean distance that we know how to do in any number of dimensions. But if you want to look at the average, you have it's not always the best way to go. For example, here I have 3 Gaussian distributions. I'm assuming you understand what a distribution is. So this giving me the probability of falling around 0, for example. But in this case, these 3 distributions, if I use the average, they will give me that I have the same thing, when I obviously don't, because the variance is different. So we have what we want is something stronger than looking at the averages. We want to see the law. The law is exactly defined by this distribution, this shape, where each point can fall. This is not easy to do in high dimensions, because we have a finite sample, and in finite dimensions, the number of possibilities where the points can fall is really big. But we have techniques to try to do this that we're now. So the first thing I'm doing, the distance not of each individual signal, between the signal happened after a specific sequence. So for example, I'm calling Y, for example, okay, so I erase the oddball paradigm. Okay, okay. So if I take, for example, E, A, E, this set is the set of all EEGs that fall when you have A, E. All the EEGs that happen after this E. I know the all symbols are here, but I mean that take only the EEG that happen after the last symbol, okay? So I have the set of all times that I had the sequence and the EEG at the end. Then I have the same, I do this for all, I'm using U, taking the strings of the same length here. Because I'm assuming that if I take a length long enough, a string long enough, they will have all the information. But this actually should be not the hardest part to test, which is, should be the size of the best side of U. The other harder questions up here. So now I'm seeing the difference. For example, I want a distance between the sets of y, this y, and for example, this y. I want a distance between these. You see that's a little different from the tree, because now I compare, for example, also things that don't mismatch in the last symbol. So I can test the same kind of questions, but can open a few others that we can test. But how to do the distancing law functions? That's not an easy question. Functional data analysis is not trivial. So the first idea that I proposed was to use the projective method as Noslen presented to you. So I have two sets of data of EEG signal. And for each signal, I project it to one dimension in a random direction. And that results in a number. That's an integral between the two. That's in a random direction that I won't get into here. But that means each function is assigned a number when I project in a random direction. And there's a theorem that shows that if I have two things in really high dimensions, basically the probability of doing that and the numbers being with different law, in law I mean the mean, the variance, and so on, falls really fast. So the larger the dimension, the more likely that it will follow the same law. If they have the same law in the signals, they will have the same law in the projections. If they don't have the same law up there, it's almost really, really, really unlikely that we'll have the same law in the projection also. So it's a good way to test it if they fall in the same place. But now I just don't want to see if they have the same law. That's not enough. I want to see the distance between the laws. So what we proposed was to do statistical model selection. That means I take a way to describe this data, in this case histograms, and I use a method to tell me what's the most efficient way without losing pertinent information to approximate this data with a histogram. So basically, I have a technique to find the best histogram from this data, and I could see the distance between these histograms, right? But now we still have an open problem that we are working with. And I project all sets and see the distance between this projection of each set. But we still have a problem, because how do I know that's projection? They preserve the similarity in law. But how do I know they preserve the distance? So we found a theorem called a lemma, actually, but it should be a theorem. I don't know the difference. But that's called Johnson-Lindenstrahl lemma. That shows that if I take if I take a sequence of random variables in d dimensions, see that I'm not assuming independence or things like that, and I project in a smaller dimension k. There's actually a condition on k that I won't get here, but I think we can work around it with a few repetitions of the project we're still seeing. That means that the distance between the projections shouldn't be much different than the projections of the original data. Okay, but there are two things. First, there's some limited, like I said, conditions on k. And two, this is still a difference in averages, right? This norm 2, the square norm. But we are developing a way to use these norms to test the data, to test the law. So how do we do this? We treat the whole set, that's the idea we have now. We have the whole set of EEGs, not only one, and project the whole set in a direction. Because the whole set has all information I have about the law of this data, right? On this condition. So it should influence the direction, because there's all information there. And see the difference not between the projection of each signal inside the set, but the projection of the whole set. And this should give us maybe a good approximation, given the finite data that we have, about the distancing law. But that is still a work in progress. If anyone knows a good paper about this lemma or things like that, I'm open to suggestions. And that's it. Thank you for your attention.
Thanks a lot. So is there any quick questions?
No, I think it's the best. No, I think the best. But is a question for me or general? Okay. Okay. She's waiting for the question. Sure. Please. Okay.
I mean, have you tried different clustering methods, see whether they make a difference or not?
Sure. I did use two. I used k-means, the classical one, and the hierarchical k-means. But for what we are doing, the hierarchical showed not actually. I used it as an example, but shouldn't because it's not the best one. Because when I grow the number of clusters, it forcibly breaks away clusters that are naturally there. So the best one seems to be the classical k-means for this, or at least maybe there's some variation of it that's good.
Okay, and I mean, have you tried to look at ways of filtering the data set so that you don't waste too much time and you don't introduce too many artifacts in your clustering due to random noise that you know is irrelevant?
Yeah, given the time of presentation, I took away a slide about pre-processing the data, but I did a few things. So each signal is actually, I subtract, so the things I done with the data. For each signal, I subtract the average of the first 50 milliseconds. So we have a baseline. And also I did filtration. I did a high pass of half hertz and a notch around the electrical noise. I think it's 50 hertz in Brazil. Okay. So I did a 10.
But you're using the whole data set up to 25 2500 hertz.
No, you're right. I actually subsampling to 500, which is usually the number that you use.
Okay, but you haven't tried to see whether there are any, because I mean, my experience with looking at data sets a while ago, I mean, is that above a certain frequency, it's mostly noise, and appears to be mostly noise, because the size of the signals is very small compared to the size of the signals at lower frequencies, and so any measurement error in the lower frequencies will just generate noise in the upper sequence. So I mean, and I was, above 60 or 70 hertz with the equipment that I was having is basically noise. I mean.
So usually in the literature, they do a low pass of about 40 hertz, but this is because they are looking at averages. So the difference of these frequencies usually disappears and becomes only noise. But since you are trying to develop a method that takes into account the variability of the data, and there's results in literature that shows that in some cases you have up to 100 hertz pertinent information about the conditions. I'm trying first to leave this information on the data because I would expect that it doesn't, because if it's just noise, it should be equal in all sets, right? These high events. So it should not influence the distance. But I can do the low pass at some point, I probably will, and see how it affects the information that I retrieved.
Yeah, so you could really filter out everything above 100 hertz and see whether you get the same results or better results or worse results. And then you probably can conclude that the information above 100 hertz is noise.
Definitely, there's a point where it's above it is definitely noise, but I don't know it. That's why I'm not doing it yet. But I will try to. The last thing I want to try is do not only that, but filter specific frequencies of.
Well, because then let me keep talking. If you have your sample data and then you append 1,000 random variables that are absolutely insignificant, that definitely makes your clustering worse because you start clustering based on the random data. And that destroys the information of the clusters that you have. I mean, so it is I think it is very important for you to try to remove all the noise that you can before applying the clustering.
I understand the question. The solution I'm using now for this question, because like I said, if I don't projecting each data individually, exactly because of that. Because some of them will be outliers that will create its own clusters. So what I'm doing is clustering the set of data, which have all of the noisy one, but the I will hope, good set of good data. And that should take away these effects of clustering outliers. But I'm also looking at trimmed version of k-means that Quest, Albertus, and Freiman developed some paper. And maybe I will use that at some point. But I'm assuming that the more general results should be, I should find something with this law difference. I'm doing simulations to see if the measurement is good, doing the analysis then, and then I'll try to do the small corrections for because first I need to solve how to do the distance in law. That's we're going, but we need to finish. Then I will start to see how the possible noise sources can influence the analysis.
Also because if you, so suppose that there was some significant component at 1,000 hertz. So that means that if you shift your signal by 1 millisecond, you will not be able to match. I mean,
yeah, there's a limitation.
That will make a big difference. And of course, I mean, the reaction time of people is probably, I mean, maybe 10 milliseconds or so. I mean,
I think it's a little faster because 10 milliseconds is comportamental difference. But I get what you're saying. Like I said, there's definitely at some point that if I filter above it, I just lose in noise. I agree. I will do these kind of things.
Yeah, it's not only that. I mean, but that if the response to your stimulus is not just a big bump in some electrode, but it is an oscillation that starts, an oscillation of, say, 100 hertz. Sure. Then if you shift that by 10 milliseconds in each signal, when you average everything out, that thing disappears. But
we're not averaging. Right? We're not averaging the data, so it shouldn't disappear.
Well, okay.
Yeah, that's the difference. That's actually really important because we're looking at the variance. So we don't do that. The small fluctuations will be there if it is they're equal to everyone.
Okay.
There will be like noise if they. Oh, sorry, I think they want to continue.
Okay, so if you have any other question, you may ask at lunch to Fernando. So you'll ask him later, and let's thank Fernando again. So now we're going to have a presentation from Paulo Passos, who's a PhD student at Rio de Janeiro. Is that it? And he's going to talk about electrophysiological signatures of context tree models in a decision-making scenario with the goalkeeper game.
Hi. My name is Paulo Passos. I'm a PhD student in physiology at the Universidade Federal do Rio de Janeiro. And I am advised by Professor Cláudia Vargas and recently advised by Antônio Galves. I have experience with signal processing, more specifically EEG signal processing. So my PhD thesis is oriented in this way, and to work with EEG. So we work along some scientific initiation students, Vinicius Maria and Camila Chaves, and this is the title of the presentation that I would do today. Okay, here. So I would like to start by speaking about this thing, this statistical learning that I've been reading recently. So statistical learning, it's a conjecture that Professor Antônio Galvez used to spoke about is that the brain can retrieve regularities from the environment. And it was studied thoroughly in the recent years, and it's been proposed to be a general mechanism for learning, and it is used in processing of sensory input. And when I say sensory input, I say the various modalities of sensory input, so auditory units, visual units, and sense of touch as well. So it is proposed that it is used in processing as well as integration of these various modalities of sensory input that usually occurs in association areas of the cortex, like the parietal cortex and prefrontal cortex. And from this branch of research, we have a sub-branch called statistical segmentation. That's I think it started with the paper from Safran, Noslen, and Newport that worked with language. And they perceived one thing that's so interesting, that in the English language, we have in the words, within the words, a greater probability of transition from one syllable to the other, and between words, we don't have a high probability, we have a low probability. So in this expression in English, we have pretty baby. So the transition from the syllable pre and t in English occurs very frequently. But the transition between t and bay occurs much less frequently. And by seeing this, they started to work with artificial language, generating this artificial language. And they start to notice that even infants with 8 months old, they start to group entities according to these measures of probability. So, and this segmentation we saw this segmentation before with syllables, but this same grouping characteristics has been seen in other types of stimuli, like basic shapes that we'll be seeing and analyzing with looking time evaluation with 2, 5, and 8 months old infants. We also have seen this with tones and analyze it with event-related potential. And we can see here it's a EEG and a mean of the EEG showing one of the ERP components that is highlighted by the author Abla, Katahira, and Okanoya. And they saw that this ERP component is modulated by the probability inside the word or the tone. It's like a word made with tones, for example. So we have a modulation of the EEG according to these probabilities. And this segmentation on this processing according to the probability measures in this grouping has been seen in other papers like this with actions, observing actions. This work of Baldwin et al. And also in this work of Hunting and Noslen, which is a study that I particularly like because they use a visual motor paradigm. So the participant watched a visual stimuli and had to press a button according to the visual stimuli. And they saw that the response time is modulated by the probability measures too. So one thing, since these probability measures are in the brain, how and where these probabilistic measures are being coded in the brain. So this is one thing that particularly interests all of us, I think. So I have this study as an example that used visual stimulus. In this study was image stimuli, as fractals. So they build a sequence of these visual stimulus, and before the starting presentation, they saw the activity when they presented this visual stimuli separately, and they saw that all of them differ. These are voxels in the hippocampus, okay? And before presenting these visual stimulus as in artificial language, they saw that pairs that occurs very frequently, one after another, start to look alike. So the hippocampus, it's probably one place that we can see this measure more explicitly. But I work with EEG, and EEG doesn't have a great signal-to-noise ratio for activity in the hippocampus. We need to focus on other areas. The neocortex is the best area. So if we can capture these regularities in the neocortex, where can we find it? So here we have a study of ABLA that saw that these statistical segmentations can be seen in the prefrontal cortex. And this is an interesting thing. I don't know if you remember what Noslen just presented, that the place where the context tree model was best estimated was in the prefrontal cortex. So maybe we have something interesting here. So, said that, we'll start to talk about the work itself. So, we have this paper that have been published this year. It's by Duarte and colleagues, the people here from NeuroMat. And they, as Noslen talked, we are using context tree models and EEG data and entities that were auditory units. So we have this context tree model that is a form of compression of data. From this, we can go to a sequence of stochastic sequence, and from this stochastic sequence, we can go to this representation, okay? And differently from what I've been seeing in the literature, in this case, not necessarily the participants will have to group things according to chunks of great probability, but to what information he needs to predict the next symbol. And this is something interesting and something that I not have been seeing too much in the literature. So we are in a frontier. I like to think this way. So in the work of Noslen, and we have auditory units. We want to pass this to a decision-making scenario. In these decision-making scenarios, these zeros and ones and twos that were different claps will become different places in this goalkeeper game that we are using, that is an electronic game. So the participant will control the goalkeeper, and he could defend in the center, in the left, or in the right. And to be successful in the game, he will need to discover something about the strategy of the penalty taker. And the penalty taker has a strategy that is a context tree model. So we are going a step further and see if with these different stimuli, that is visual and not auditory units anymore, and in a situation that he has to interact, if we can see he learning and how he is learning and what he's learning and what is what interferes with what he will learn. So here we have a work that is in the very beginning that I presented in Brazilian Society of Neuroscience and Behavior. And what we did to now is basically writing routines to make things as best as we can for the analysis, statistical analysis, and etc. Here we have the error from the 6 frees that we used. We collected a group of 37 participants along the last year in the Rio de Janeiro and here in São Paulo with the collaboration of everyone. And we saw on very basic statistics that the performance of the participants differed significantly from the statistical procedure that we applied. But it's something based on performance till now. We don't estimated the context tree yet. We have to do all of this. And we saw that the performance differed, and we saw that the response times, here we have the response time for different trees, that they tend to become shortened, the response time, as the time goes. And as we see the performance, the behavior of the performance, and the behavior of the response time, we can see the participant is learning something about the context-free models. We don't know yet what it is, but something is. And so we are working with the behavioral data, and then we work with EEG. And here I'm presenting the context-free models in a different type of presentation that I propose to Claudia, because generally we see the context tree, the oriented label tree, and a table of probability measures. And I think these, in this way, we can see everything. So, basically what I've been doing till now is making a setup to perform what we need to record the EEG signature and put it together with the goalkeeper game. So we recently, finally, have the setup ready. So we have a special monitor for better signaling the stimulus presentation time. We have a way to combine the triggers coming from the goalkeeper game, and we will use a 32 channels EEG and an EEG adapted for monitoring eye movements, as well as a Cedros keyboard that will that make the response time better. So what is our hypothesis, what we are working with? We will assume that the information about which context tree the participant, in which context the participant is currently, can be retrievable from the EEG before the decision takes place, okay? And for this, we need that the different context trees imply different EEG signatures, okay? And we must use, to do this, we must use a context tree model that allows fast learning from the participant. And we must use a context tree model in which every context occurs sufficiently for applying the algorithm. So we have a number of trials that is not enough, we don't have a good estimate. It's simple like that. And we must take care with confounders. For example, we have the lateralized redness potential, for example. We know that from the EEG, we can retrieve which response the participant made according to which effector they used, okay? So if we apply any statistics in this scenario, you can say that the signatures are different because of the response and not because of the context. And this is a very big problem for us. So one possible solution that I found to now is using a tree in which different contexts have the same response for at least two contexts that will be tested against each other. So we can precise where in the time the signal will tell us the information about the context and will not pick up the part of the signal that will tell which is the response, okay? So we have a trial configuration like this. We have a ready section in each trial, okay, in which participant doesn't respond. And we have a go section. This ready section, it's 1 second because the lateralized potential starts to appear at approximately 1 second, half second. So if we get 1 second, maybe we can see much more. And then we have a goal section that don't have a time established, okay? So the participant can respond wherever he wants. This is not a problem as we can think for the number of trials because from the experience that we have and we presented in Brazilian Society of Neuroscience, and the participants tend to diminish the time that they respond. And it's not a big problem. So we have a feedback section in which that is the animation that tells the participant if they are successful or not in the present trial, and a wait section that was proposed by Raimundo, one of our collaborators, for vanishing with the process of visual stimuli. So we have this trial configuration now. And as I present here, I have one possible context tree. I think this is the type of presentation that I like, because here we see the probability measures and the context, and we know that is a tree. So we made a first recording in a couple of weeks before, okay? And based on previous results for 960 trials, the context with minimum frequency occurred 96 times, and the one with higher frequency for this context tree model occurs 320 times. So in this case, we have a number of trials that is good. And we made the recording in the experiment we estimated before that the experiment should last at least 1 hour and 20 minutes. It's 960 penalty kicks. It's too much. But this estimate is in agreement with what we saw in the recording, and the participant thinks it's it's awful. But for this tree, not as awful. And we made also a second recording with one of the trees we already used before, that was presented by Noslen. And from the trees, in the tree we have some problems, because in this we had a number of trials we need. We have the situation, we need two contexts that we must compare that go to the same results, same response with the same probability. Here we have this condition too. So we have 1, 0, 0, and 0, 0, 0 going to 2, both of them. And, but okay, what happens? Based on previous results for 1,080 trials, the context with minimum frequency occurs 24 times. 24 times. It's too low. And the one with higher frequency, 270. So We estimated that this experiment should last 1 hour and 30 minutes. That was approximately what it was. But we have this problem. And I don't know if this was the tree that had that was retrieved with good as a good estimation. It was okay, but it was retrieved in the auditory in the auditory paradigm. But looking at the performance of the data we already had analyzed for the Brazilian Society of Neuroscience, the performance in that tree is not good. Yeah. It's a difficult tree. Everyone who played it said this. So up next, we want to reconstruct the context trees from the behavioral data, analyze the response time of the behavioral data, and see if we can apply the algorithm for retrieving the estimate of the context tree from the subjects, and look at the data from the recording to see if everything is okay, then continue the experiments to see what happens, okay? And this is it. Thank you all for your attention. This is our team at ENDC, and thanks to the funding agencies.
Thank you very much. So, is there any questions for Paulo? Yes.
Maybe you say something and I didn't realize, but can you come back in your last tree, please?
Of course.
This tree, it's almost our tree, let's say, but in your 2-1 context, you have like a deterministic option to go to 1. Is it in purpose?
Here?
No. 2-1. Yeah.
2-1, what?
Yeah. Your transitions probability are not the same as ours. Is it in purpose? There is a special reason you took like that?
I have been messed with the representation. It's the same tree. I must
so after a 2-1, you don't go to 1 with probability 1. This is what you're telling.
I don't remember exactly the representation of the context tree.
No, I'm not speaking about the representation. I'm speaking what happens with your experiment after a 2-1.
After a 2-1, go to 0, probability 1. It's here, 0.
Okay.
This tree, it should be here.
Okay.
But in all others, it's okay. So we go to 0, probability 1. Yes. Okay. Yes. So, another question?
No other questions? Sure. So let's thank the speaker again. So we are now going to have a talk of Yanina Leon, who is a master student at the USP in biology, and she's doing her master thesis. She's going to talk about statistical learning in the Parkinson disease.
Good morning, everyone. My name is Yanina. I'm master student of Professor André Frazão. And our research is about statistical learning in Parkinson's disease. I will start or try to explain what is Parkinson's disease. Parkinson's disease is a neurological and chronic disorder that results primarily from the death of dopaminergic neurons in basal ganglia, resulting in movement disorder, and is considered as idiopathic because it's had direct relate with genetic, and only 3% is explained of genetic factors, and the other percent is explained of environmental factor too. It's considered a progressive because it has a direct relate with the age, and for this reason is considered a complex disease. Parkinson is recognized as the most common neurodegenerative disorder after Alzheimer's disease, and the prevalence in Europe is more, if you can see, if you can see, is more frequent in Europe than South America. Maybe it's related with the age. I try to explain how is the motor symptoms present in Parkinson's disease. This is a represent of the circuitry of motor symptoms. For example, motor symptoms is a result of the Glenn basal disturbs or dopaminergic cell loss. This is basal ganglia is in the deep of the brain, and it's representing here, like a striatum, globo pallido externo, substancias, subthalamic nucleus, and when we have or when we lose dopaminergic neurons in substancia nigra per compact, we have deficit to connection with the striatum. Then striatum have less inhibition to globo pallido interno. Parallel striatum have more strong inhibition to globo pallido externo. Then because has loss inhibition here, the result is a weak inhibition to subthalamic nucleus. The result of this imbalance is a strong inhibition to thalamus, and then the result of this imbalance too is a weak connection to the cortex motor. For explain, make an analogy with an example. We can use, or we can think that the basic ganglia are a dam. This is, for example, water, and the dam is contained to the water. Basic ganglia action is to contain motor programs, a lot of motor programs. For example, walking, for example, move the hand or dancing. And basic ganglia always is inhibition these motor programs. And when you have imbalance in basal ganglia led to, for example, led to motor programs like walking or dancing in the same time. This is the reason for we have motor symptoms, like bradykinesia, that is slowly of movement, hypokinesia, this is a reduction in movement amplitude, akinesia is the result of absence of normal and consistent movement, freezing, this is the inability to begin a voluntary movement, and loss of motion automatic, when the people can't to make a voluntary movement. But Parkinson is not only present or only have motor symptoms. A retrospective study show Parkinson start 20 years before the diagnosis is making. For example, the people who have Parkinson in the time zero, the people has a diagnosis with tremor, freezing, or bradykinesia. But 20 years before, the people present constipation, problem with sleepiness, problem with hyposmia or depression, and like that. And this is evolution in dementia or other symptoms. When the people have motor symptoms, is evolution in fall 2 or freezing. This is a problem because there are other disorders associated to Parkinson's disease, like sleeping disturbs or depression, dementia. Dementia is about 75% to 80% patients. And after 20 years of these people evolution in dementia. And 92% of people with Parkinson's disease have cognitive impairment, like problems with memory or attention. Currently, Parkinson's disease medication treats only motor symptoms and not halt or retard dopaminergic neuron degeneration. And we don't have other treatment for cognitive impairment. And what about basic ganglia and implicit learning? Experiments in people with Parkinson's disease relate correlation between motor performance and implicit knowledge acquisition. And we call automaticians that when increased performance through cognitive monitoring, like cognitive monitoring like attention, or when the people use more cortex for in text. And the relation is loss of the neurostriatal dopaminergic neurons relate at loss of automation, then loss of implicit learning. Our justification of our research is motor symptoms that are the basis for the diagnosis for Parkinson's disease occur when 70% or more of striatal dopamine has been lost. And the second is there is no biological marker for Parkinson's disease. And finally, there are difficult in management of symptoms as later stage. But but the diagnosis is based only on motor symptoms. Our hypothesis is progressive dopaminergic loss in the basal ganglia is a pathological feature in Parkinson's disease, which results in dysfunction of automatic motor response. Our work assumes that loss of automaticity can be measured before the motor symptoms are installed. This measurement can serve as an early diagnosis. But we have concerns like age, for example, have a direct relate with Parkinson's disease, and the age has a direct relate with senile dementia. Parkinson is related to with other disease like a depression, like problems with sleeping, and because share the same neural circuitry. And because it's a progressive disease, symptoms get worse as you get older. And for our research, we have two goals. The first is a result that Empire group with Professor Rocky and the Professor Gubi is present here, the Professor Maria Lisa, and my Professor Andrea Frasant. We have to test, we had test whether goalkeeper gain can be used under dual text to predict erosion in gait automaticity in the early stage of Parkinson evolution. And the second goal is evaluate the automaticity in implicit learning text of probabilistic sequence in Parkinson's disease using the goalkeeper gain. We have to use the goalkeeper gain and mock evaluation This is a cognitive test. And we have to use motor evaluation too, like a dynamic gait index, or text and time as and go, or dual text too. And at the moment, we evaluate 150 participants between two groups. The first group is people with Parkinson's disease in 3 stages in Hohenjahr labels in 1, 2, and 3, and the control group. For our study, we adapt the goalkeeper game that you know, and Noslen explained too. And we use 3 phases. In the first phase, this is the motor baseline. We try to record the reaction time of people with Parkinson's disease to the control group for normalize the reaction time. In the second phase, we use the learning phase, and in here, this phase is programming by the context tree of Noslen, with the help of Noslen, and the objective of this phase is to record the responses or recording implicit learning in Parkinson. And the last is the memory phase, where recorded the explicit learning. Goalkeeper game use finite alphabet set A, content 0, 1, and 2. 0 represent left, 1 center, and 2 right. And for the baseline, we use a determinate sequence like that, and each repeat 1, 0, 2, 1, 0, 2. It is easy because Parkinson's disease have to learn more easy. And the second phase is learning, and it contains 102 trials. And the people, this is the result of the context tree of Noslen. And the last is a memory. We use deterministic sequence of 4 elements, like a 2, 2, 1, 0. We present this sequence before the participant playing the game. And he have to memorize this sequence for response. But the question is, it's possible to obtain enough data to identify the premotor phase for Parkinson's disease? We don't know, but our preliminary result is goalkeeper game is at least as good as the MOCA test. This is a cognitive, do you remember? For predicting the cause of motor tics. Goalkeeper match was a better predictor of the GI. This is a motor test compared to MOCA, with a ratio of 65% for goalkeeper match and 56% for MOCA. Other preliminary result is this figure represent performance between people with Parkinson in the middle stage and people control young. And in blue, it represents the context tree that the people playing. For example, this is a left, center, right, left, center, right, and repeat like that. And in red is error percent of the response of this group. If you pay attention, the people with Parkinson's disease in the first stage, in the first trial, the people is not learn the sequence. And finally, the people don't, the performance is equal to the first stage. And people young maybe learn in the sequence who have more probability to appear. In the finally, have 0% of error. Maybe in this result or this game, we can use for make a early diagnosis, or can we use the goalkeeper game in the medicine for make a early diagnosis. Well, this is all. You have a question? Thank you.
Thank you very much. So is there any question for Yanina?
In this last picture you show us, it's in the deterministic sequence, right? Because they learned with 0 mistakes in the end, the people without the Parkinson's disease.
In here?
Yes.
No. This is
How can they have 0 of mistakes if it's a stochastic sequence?
yes, this is a stochastic. This is here. This is a tree, contrast tree we use for
Okay.
this phase.
Okay, can you come back to the picture? So I don't understand why they.
In blue is only a represent of this the trials.
Because you're not changing the 2, right? Because in your sequence you change the 2 for 1, right? With some probability, or 2 for 1 or 0.
For 1, yes.
Yes.
Uh-huh.
Okay, so in the end they are not making any mistake because you are not changing any 2s. This is the point, right?
Uh-huh.
Okay. No, it's because everything is deterministic.
Yes,
is-
now
okay.
becoming deterministic.
Yeah, you change it just a little bit the 2s, and in the end you are not changing any 2.
Yeah.
So this is why they are making no
Mhm.
mistakes.
Uh-huh.
It's a small comment. There is another PhD fellow working with Parkinson in a different way. It's Arthur Valencio, who is supervised by Stoffer here, and he's working with people in the Hospital das Clínicas, and people with Parkinson and with stimulation, deep stimulation. I guess deep stimulation. Don't know where. So Fernando, say what are we doing?
Okay. Sorry. Okay, so we're working with a neurologist and we are working with neurologists and neurosurgeons in Hospital das Clínicas that do a procedure where put an electrode at the bases of subthalamic region that she mentioned. If you have in the slides, you could bet. In the same region that she presented. And this cancels the atypical pathological activity there. That's the assumption. And we are working in how that affects the cortical functioning, the cortical behavior of the brain, to see if the Parkinson and the electrode, because we have controls, are affecting the physiological behavior of the other cortical regions that we can measure with EEG. And to do that, we're using a paradigm of moving and freeze point people. How would I explain that? Is this similar to people walking and people standing still, to see if the difference in the brain when seeing these two things? I guess that's it. Okay.
Okay, so is there any other remarks or questions?
MoCA takes into account only cognitive parameters, or it is combined in the MoCA index cognitive and motor?
No, MoCA only diagnoses dementia by cognitive impairment. But the relate of our study is these motor programs is not only motor, because for example, when you have to learn for the first time to go by bike or dancing, you have to pay attention and use more motor cortex for what movement you have to do. And it is cognitive. And they becoming automatic when you use or when you try and you learn. And this is the reason if the people learn a sequence becoming automatic when they have more trials. Maybe in the first moment is cognitive, just a lot of cognitive resource, like attention. But when the people have more opportunity to learn becoming automatic and have a direct relate cognitive and motor. This is the reason for we use MoCA too.
Okay, so any other questions? No? So Fernando has some announcement for this afternoon, but first let's thank the speaker again.
So thank you everybody for coming to and presenters for presenting. We will come back at 2, not at 1.5 like in the chronogram, just to keep everyone at 2, okay? And yeah, to feed everyone, so everyone is properly fed. And just announcement, in the second part, with one exception, all the talks will be about some people call the bottom-up perspective or simulation of neural networks and so on. This in the morning we didn't mention, but the talks in the morning were about the statistician brain, and then in the afternoon about. I think Guilherme is also. Yeah, sure. There are few sections, but mostly we divided. Yeah, but no, but in the afternoon is that what I'm saying is in the afternoon is people working with. No, but that's what I'm saying.
So maybe your pattern is not.
No. That's the part. In the morning was the statistician brain. In the afternoon will be neural networks. Okay, and so people are listening YouTube. In the afternoon, it will be another link that was sent together that you need to watch to follow, and we will start at 2. Okay. Thank you, everybody. Good lunch.